and so I'm going to talk about topological sigma models and this is the work done with a graduate student, Felix and Loganayagam, who is now in UC Davis. Many of you here have already heard various versions of this talk, especially over the last month in NSM, in Goa, in QFT questions, workshop, and so on, and elsewhere. So, what I'm going to, but always there are things that need to be said, and which I never get to say because of time constraints and the technicalities required. So a basic chunk of the talk would probably be something that you guys have heard, if you have heard any of these talks before. But I try to say and emphasize some things which are not emphasized often by us, because of time constraints before. Okay, so let me start, as I usually begin such talks, by drawing these three boxes, which kind of tell you the basic kind of subjects that we are motivated by, the kind of questions that we are motivated by. The first box is Schwinger-Keldysh. So this is a formalism named after these two gentlemen, which is deal with non-equilibrium, but it could also be near equilibrium. Quantum field theory. So the question is that quantum field theory, which does not have a definite temperature, either zero temperature as it is usual, or a finite temperature as in the thermal field theory, but it has some, it's slightly away from that state, the thermal state, or it's very much away from any thermal state whatsoever. And then how do you think about the physics of the quantum field theory, and how do you think about the correlators in the quantum field theory, and what is happening in the quantum field theory? And there's a formalism to deal with it, which is basically a path integral for the density matrix, which was developed by Schwinger-Keldysh, and density matrix is the correct thing to think about here, because in general we would be interested in mixed states. And that's a whole set of ideas which are there, and there are various things which are not quite understood about it, in our opinion. And one of the things is to just try to understand the formalism better, and whether one can understand, for example, to the same extent that we understand the zero temperature quantum field theory in President Schroeder or something. How do we do renormalization and running and so on and so forth, which are not quite understood in this formalism. Okay. So the next box has to do with fluid dynamics, which mostly I mean relativistic fluid dynamics, is what I'm going to say, but though most of what I'm going to say applies also to non-relativistic fluid dynamics. So this is the IR limit of near equilibrium quantum field theory. That's one way to think about it. Okay, that at large enough temperatures, any near equilibrium state looks like a fluid state in a quantum field theory, if you look at only the long distance physics. Okay, and these two are obviously related, and there is a reason to talk about them in one go. In some sense, these two are related by, if you wish, so, like I put that in quotes because we don't quite understand what does RG mean in this situation. But at least we think that we understand physically what is happening, which is that the long distance physics of this near equilibrium quantum field theory is described by some fluid dynamics. Okay. So the third has to do with black holes. I will be restricting myself to large areas, though what I will say probably also applies for many other black holes and anything with horizons like this, for example. Though let me just confine myself to large areas black holes. The reason this can be taught in the same way this is that first of all, there are particular kinds of quantum field theories which by ADS field are related to gravity in ADS. So that studying these states is often translates very nicely to studying the black hole states. And for the same reason, there's a relation between these two also, which sometimes gets called as relativistic correspondence. Okay. And so there's this whole set of ideas, okay, and all these three subjects, if you wish, okay, bring their own peculiarities. So it's clear from various things that I've said, from various CFD, from our usual ideas about logistic physics and so on and so forth, that we take for granted that these three ideas are definitely related, okay, and they are very closely and intimately connected with each other. But if you start looking at them more carefully, you start finding some peculiarities. Okay. So let me write down the peculiarities in each box. Okay. So the peculiarity of Schwinger-Keldysh is one of the major peculiarities is doubling. Okay. So this has to do with the fact that to describe density matrix, you have a broad copy of the fields and a Ket copy of the fields. So compared to the usual path integral, okay, should not draw boxes. Okay, compared to the usual path integral, let's say the same path integral, the Schwinger-Keldysh path integral involves doubling. It involves two copies of fields, not just one copy of the fields, and that's a very characteristic feature of Schwinger-Keldysh. Okay. And another characteristic feature, which
sorry, Logan, I might be preempting you, but will you define the Schwinger-Keldysh path integral?
Yes. I'll define it. Yes. So I'm just saying some general things. Okay. So I'll define it. So there's another important feature which is important is that so Schwinger-Keldysh path integrals are describing some near equilibrium quantity theory. They are describing some real-time dynamics, the evolution of such mixed states, and hence at least the near equilibrium situation can often be thought of as analytic continuation of Euclidean path integrals. Okay, and the Euclidean path integrals have Euclidean periods imposed upon them on the imaginary time, and when you come back to the real time, that means certain things. That means certain constraints. These constraints are sometimes called as the KMS constraints after Hugo, Martin, and Schwinger, who first wrote them down. And those are another constraints which are satisfied by Schwinger-Keldysh correlators, especially if they are evaluated over an equilibrium state. And that is also a very peculiar feature of Schwinger-Keldysh. There are very peculiar features of fluid dynamics also. Okay. One is, you can say, the main thing is actually dissipation. But the dissipation is not any old dissipation. There is an entropy current associated to it. Okay. And your dissipation is manifests itself as this inequality being greater than 0. Okay. The entropy being produced. Okay, and so there's an existence of a local entropy current, and then there is and the entropy is created.
Is there always a local entropy current? I mean, case by case, you might be able to construct it, but is it always the case?
In fluid dynamics, it is believed that it is. Yes, there is an entropy current. I mean, that's the standard formalism of fluid dynamics, that there's a local entropy current. And,
I'm sorry to interrupt you, but I know that you have Navier-Stokes equation, but that's d mu t mu nu equal to 0, energy moment of conservation. But entropy is not any sort of conserved or whatever we know. So why should there have to be an entropy current?
Why should there have to be an entropy current? That's a very, one way to, at the fluid dynamics level, it's just an axiom. Okay, which is important for various things. I'll just come to it in a moment. But there is, if you're asking why there is an entropy current from the microscopic point of view, okay, it has to do with some of the things that I've written down. Okay, in a way that is not understood. That's what I'm coming to.
Well, please do go on. But I also meant just at the level of fluid dynamics, fluid mechanics. That is, I understand that you have degrees of freedom which are the for velocity and temperature and so on. And I understand that energy momentum, of course, is conserved, so you get Navier-Stokes equation. But why should you be able to build an entropy current out of these variables in general? This is not.
Yeah. So if you don't impose, okay, so it's an axiom, as I said in fluid dynamics. Now we can ask why anybody would like to impose this thing. I mean, one is, of course, if you impose that as an axiom, you get fluid dynamics which is sensible and which matches with what we see next to it.
Isn't entropy, the idea of entropy increase in thermodynamics, plus some locality, forces you to have a current description. It flows from here to here.
What I meant was, if you have a conserved quantity, then it makes sense you have a current, because locally, say the charge changes, then it must be because there's a current going on.
Yes.
But if you have something which is not conserved, then why does there have to be a current? It's just not conserved locally.
Okay, but it's produced locally. It's never destroyed locally. That's what the statement is. See, del dot J is equal to 0 tells you that the production in any little pillbox is always positive. Now the second
del dot J, this is the spatial gradient, right?
No,
full one. This is the full. Okay. All right. Okay.
It tells you that the production in any little region is positive. It's never, in a little region, the entropy increase plus the entropy that goes out is always positive. Okay? So it's a local form of the second law of thermodynamics. Now you can ask, is it possible that the second law of thermodynamics applies even though the local form does not apply?
Correct.
Subject to local motion.
I mean, there would just be entropy density which increases with time.
But the equations of motion are local. So it would be very hard for that to work. In particular, you can take fluid dynamics and couple it to local sources. For instance, a local metric that comes to stress as a local. And you will have to have that this was true for every fluid flow. And it will be very hard for that to work unless it's happening locally. Because you can mess around with what's happening here without touching what's happening here by taking sources. I think that's a rough introduction. Would you agree or not?
Yeah, but at the end of the day, it's just put in. It's put in because it's what we see, and it's sensible. And as I would also say, it's also sensible. Somehow, whenever you try to derive fluid dynamics from a microscopic theory with these kind of properties, you always get something which is,
also, if you make various assumptions just about the existence of equilibrium,
which is basically this, it's related to equilibrium. So,
but even without any dynamics, just assumptions about equilibrium, then you can use that to construct an entropy current, which always obeys this property.
You're giving me talk.
Sorry.
Can I ask Sandeep's question again? Sorry, I thought that, and I've just realised I must be being stupid, but I thought that fluid mechanics was a flow velocity and a temperature which can vary locally, subject to d mu t mu nu is 0.
Yes.
And that seems to be
I'm not subject to this.
And at what point do I even define an entropy current? Do I also have to define entropy that can vary locally?
Yeah. So you have to define entropy which can vary locally. What this does is that it cuts down the space of allowed t menus that you can write down.
What David wants to hear is that it's a function of u and
Yeah, is that interesting?
Yeah.
So it's really I define t mu nu and the entropy current both as a function.
Yeah.
And I'm also not familiar. I mean, if you open the beginning of Landau relations, you talk about T mu nu, but not J mu affairs.
But he shows that the viscosity is positive by demanding this.
I see. Then he constructs a J mu as is it?
Yeah. For example, yeah. So why can't you allow negative viscosity? There's nothing in symmetry reasons. There's no symmetry reasons why you can't allow negative viscosity in Navier-Stokes equations, but you just don't because you impose this. And then there are other constraints.
So an even more basic question, if I go back to thermodynamics, the variables I use to characterize a system are temperature and entropy independent.
No, you usually calculate it by giving, say, pressure as a function of temperature. So you have some equation of state.
I have an equation of
State. Where let's say you have no other conserved charges. Okay. We can make conserved charges, we can get potentials and so on. But if you have no other conserved charges, then temperature, you can take temperature as a basic variable and everything you can. Yeah.
So So just one question. So in thermodynamics, going back to the question, T and S are some of conjugate variables, right? You
Yes.
don't use both of them at the same time. So you're saying that when you go to fluid dynamics, you're going to use both of them at the same time?
No.
Locally.
So there's going to be a current, an entropy current. Okay. But the entropy current, for example, would start off like some, let's say if P is your pressure function, it will start off by saying, like having some in that sense, like this thermodynamic expectation that the entropy is dP by dt is true.
Even in thermodynamics, once you know the temperature, you know the entropy. So you know the temperature and velocity, and therefore you know the entropy.
So the dot dots involve derivatives and so on, so that if you take velocity to be just constant, you take thermal equilibrium, homogeneous state, then those layers are not there, and then you just get what you usually.
Right. I guess I was asking that usually in fluid dynamics you think of some local equilibrium. So the question would be, is that local equilibrium given by your local temperature or local entropy? And you're saying somehow both
it's given by a local temperature and an equation of state, which gives you a local
entropy.
Yeah, which is related to the equation of state in a very specific way. Yeah. So this entropy current is also related to, should I say, the existence of hydrostatics, which is about time-independent solutions in fluid dynamics. Okay, the existence of equilibrium solutions in fluid dynamics. So this is the second one. And there's also something else which is often what we ask about, which is how, let's say, noise or fluctuations in fluid dynamics, how are they related to the dissipative coefficients in fluid dynamics? Because it's a near equilibrium system, okay, which is locally in equilibrium, okay, we would expect that there are relations which relate noise, like in fluid dynamics, the fluctuations in fluid dynamics, okay, the Avogadro surplus fluctuations in fluid dynamics, and the dissipative coefficients by something called as something which we would call as a fluctuation dissipation theory. So this is all. So these three guys, okay. So I've written down three things. One is an entropy current with the second dot, okay, and second is the existence of hydrostatics, and third is fluctuation dissipation. These are very. These are the kind of usual things that one looks at when we look at the infinite limit of near equilibrium quantum field theories. This is the kind of things that one imposes and studies them, and they're all very closely linked, and often they, with some assumptions, often they imply each other. Okay, and the question is that like how are these related to the ideas here?
Because I have a small question, if you don't mind. So in the second box, fluid dynamics, suppose I have some relativistic fluid dynamics, how do I know that in long time it will actually relate the hydrodynamics? I mean the static solution. It's a very difficult formal question, but we assume that, I suppose.
I think we assume that if the forces are turned off, okay, and we wait, like you don't force the fluid,
Should happen.
then it settles down, and it seems a reasonable assumption.
I agree.
See, but one cannot, given that the entropy only increases, you can't prove it.
Often that is a very strong constraint, and it all for example, whenever you are able to prove that it approaches equilibrium, it uses some version of this entropy statement very okay. But there's nothing which you can. I mean, in principle, you can think that the entropy doesn't increase, but somehow the entropy stays almost constant, and it just goes on doing whatever it's doing.
But for simple hydrodynamic dispersion relations, you can prove that, right? Yeah. There's hydrodynamics on a sphere from entropy increase. Del dot J is the sum of squares, the lowest order. You set each of those squares equal to 0, unique solution.
Okay, so this is the set of things in the second box. Okay, so let me talk about some things in the third box. This third box, which is about black holes, is also very.
No, it's true.
It's not true. It's also very confusing. Okay. And one of the most important things about black holes, as we all know, is the presence of horizons. Okay. and hence also interior. And relatedly, like sort of think that, for example, if you have something like unitarity in black hole evolution, there should be some version of black hole complementarity. So it's not yet clear what that means, but at least in some sense we have a rough idea what it is. Okay. So there are, and these are things that are very specific to black holes. I mean, the first thing is that black holes have entropy. They have their Hawking temperature, and they have, and these are due to the fact that they have a horizon, basically, okay, the structure of the horizon in general relativity, and they have an interior, at least classically, okay, and somehow there's some kind of a complementary description between the two. Okay. Now the question is that like how this.
Sorry, but this part I didn't get. So the fact that they have, how does the complementarity tie in with all of this?
Yeah, it's not. I mean, the complementarity. Yeah, and like there have been proposals, for example, by Subrat and Rikos that the complementarity is implemented by some kind of W. Okay. So which is
that is a bit of a conjecture.
Yeah.
That for the perfectly equilibrium state, yes, you have the double black hole form collapse.
Well, they would argue that
interior.
Yeah, but they would argue that even for a black hole, which is inside collapse, it's related. I mean, at least
but if that's the case, it's only a very late time, and so on and so forth. So
yeah, let me come to it. Okay, so the question is about all these statements. So I have written down various ideas, okay, which are all kind of very disparate ideas, okay, and not always talked together. Though like they have like similarities and they relations.
Can I ask something? Sorry to interrupt. So the last box is actually there's a large n plus an order 1 state in one direction. So in the upper boxes, I mean I can see on the top box something like that actually.
Fluctuation dissipation is a bit like that.
Order 1. That's the point.
Yeah. So let me just try to list. I mean, so this looks like a stream of consciousness kind of things where I am just listing everything. But I would like to say that there is a long list of results. Okay, even before we started thinking about the subject. Okay, which strongly suggests that these ideas are all very related, okay, and it's often forgotten, like I mean, even people who know all those ideas don't always put together. So let me just say one by one, okay. So there's an old result, okay, which I guess goes back to Onsager, Kubo, and many other people. And recently Jalzinski and so on. Okay, so I'm not being very fair here. So which basically roughly says that the fluctuation dissipation, so is very closely related to setting. So that says that this is very closely related. Okay. And then there are.
I did explain that a little.
So, well, in the sense that like if you impose some kind of fluctuation relations on various processes that go on in the near equilibrium theory, okay, like which basically, for example, one way to I'm kind of. Some basic distinction between fluctuation distribution and fluctuation relations. So if you have something like like an entropy, like a destroying process is statistically exponentially suppressed in a very specific way with respect to an entropy producing process, then you can show that something like second law should be true. But so for roughly this has to do with statements of this kind, okay, where you prove something like this. That is, this is the entropy production in a process. Okay. So the expectation value of entropy production among some similar processes is 1. This is a bit crude. I mean, as Jardinsky and so on have argued, but this is fine. And then from this, you derive something like saying that the entropy production should be positive. Okay.
So from integer minus delta expectation value is that 1?
Yes.
So then.
So this is just saying that
the expectation value is this.
Yeah. This is some convexity of the exponential function, which makes sure that you can use this and then get that. Okay. So that's roughly the thing. Like I can tell you what it did, but there are various results of that kind of this flavor. Okay, which go back in.
Sorry, just one. How is this sort of relation related to the fluctuation distribution thing?
Okay. So what you do is like. So what you say is that let's say this is the probability of. I won't be able to make these various things. So what you do is like you argue for something like this. Let's say that the probability that you have an entropy distribution minus delta is exponentially suppressed by this amount. Just like that. And then we just use equal to 1, and then we can do
so that initial statement somehow is related to the fluctuation distribution.
Yeah, this is a fluctuation relation, okay, which is often also closely related to fluctuation distribution theorem.
Yes.
Okay. The fluctuation relation, I mean, sometimes people distinguish because fluctuation relation often are supposed to be. I mean, there's a way to take this even very far away from it also. But I'm just trying to give you. I'm not trying to give you any particular statement. There is a whole slew of results of this type, okay, which basically roughly say something like this, okay, where you have to quantify what you mean by here, like you take a particular version of it with particular assumptions, and then you prove, okay. And one of the most careful things is by Jardinsky and various things that are followed from this work. So this is called the Jardinsky relation and work relation and so on. So anyway, so the point is that there's a whole set of results which tell you that this is true, okay. And there are also a whole set of results, including Schwinger-Keldysh and various other people. This kind of stuff keeps on getting reinvented. Okay, it basically tell you that in some sense the KMS, which is the relativistic condition, or let me also call it the thermal invariance sometimes. Implies fluctuation dissipation theorem. This actually is easy to show in the sense that you can just look at the KMS conditions and you can show this is a textbook stuff which is often said that you can use the analytic integration of Euclidean periodicity to show why fluctuation dissipation should be true. Okay, at least for fluctuations about equal. Okay, good. So then there are various other works starting from Mattei-Quillen in mathematics. Okay, actually Mattei-Quillen has interpreted the idea of drifting, and fluid dynamics people know it under this name, Martin C. Rose, okay, and various other people, okay, and in N equal to 4 this was Markov-Witten and so on. Okay. So these various works, what these various people have shown is a particular thing which says that the double So given a set of equations, and the equations that Baha-Witten were interested in was the instanton equations, and Martin-Rose were interested in the fluid equations itself. Okay, and Jeffrey formulated as some equations, whose moduli space of solutions you want to study. So given a set of equations, okay, you can write down a doubled topological theory. Which localizes it. Okay.
So for all types of equations, how should I get this?
Yeah, I mean, almost kind of all types of equations. This is kind of so there's a set of equations, which have. So you can there's a very nice way in which in the space of solutions of those equations you can write down a double topological theory which captures the space of solutions, which kind of count the space of solutions. That was what Baha-Witten were interested in, to write down something which counts the number of instances and the dimensions of moduli space and so on. But Martin-Rose were interested in trying to understand the space of fluid solutions and trying to write down a path integral for them. Okay, and quantizing them in some sense. But the point is that if you consider space of solutions of a given set of equations, often you can write down a double topological theory which localizes to exactly those equations. Okay, and the double topological usually means that you have a Q and a Q bar, okay, such that Q square is to 0 and Q bar square is to 0 and Q bar is anti-commuting. Okay. And your action is Q closed and so on. It's a topological theory of Witten type or homomorphism.
When you say localizes, you mean then that the states where Q is 0 are the solutions of the equation.
Yeah. So somehow if you kind of do a path integral over the double topological theory, okay, with say some insertions of operators, is same as calculating correlators with these equations.
Calculating correlators about solutions
of these equations.
What is the common between these type of equations? What type of equation you can do this?
So, I mean, this is pretty much can be done for any set of equations. If the set of equations have some gauge invariance, there's some subtleties which Baha-Witten worked out mainly. Okay, and that's the reason I'm quoting them. But the main thing is, you can just write it down for any set.
Where is the supersymmetry or whatever coming from? For any set of equations, you can do this. I don't know, it seems strikingly general.
There is one context in which fairly general result can be proved. Like if you start with some first order time differential equation and add some noise term to it, make it into a Ranchabon equation, then that can be made into some functional integral with this extra auxiliary supersymmetry, which is called the Parisi-Sutras supersymmetry. And that situation can be made into supersymmetry path integral, which has exactly these properties that he is saying. And then the localization of that, it gives you back the original equation. Okay, so that's known. But I think your example is a broader class of.
Yeah. For example, that like Parisi-Sutras, various results in stochastic quantization. In fluid dynamics and in Baha-Witten theory, there is localization in, actually, I would say even Fadi-Popov trick itself is actually an example of this. But there's a general result of very, which is rediscovered.
It's in common between these equations. What is one thing that connects this? And that you can say, you need this property for this last thing to multiply.
No, these are just a set of equations. Maybe you need that the moduli space is not like too wide, in some sense. Okay, but it does not have if you go to some, like roughly around each solution, same number of solutions. Or even that is not quite necessary. But at least it's not too wide. But anyway, but I think.
What I think your meaning is that there is a variety of equations we know, which can actually be discussed this way. I mean,
Yeah, actually,
the method is not the same for all. I don't know.
Well, okay,
If equal to F dual, I know the method is different than what Compton says.
yeah, but the method is not very different.
Perhaps we have not seen that.
Yeah.
Maybe you're right. There is some connection which at least I haven't seen. That's all.
Yeah. So the thing is that I think this is I don't know of a particular constraint which is actually this equation. When Atiyah and Jeffrey wrote a paper, just after topological field theory came about, and about trying to apply mathematical formalism and writing down these field theories, they were just looking at some modular space of. So they had in mind some general set of equations, which are which cover almost various things that we know, and this has been applied in various ways. I mean, it's a kind of it's the engine behind various things in topological field theory, localization, all that stuff.
At some point, you give us one example.
Yeah. So, okay. So then so the reason that I'm saying this is that it tells you that there's a set of equations here, fluid equations, and you might ask why is there a doubling? How is doubling related to these fluid equations? And this shows you a way, that why fluid equations might naturally be described by some kind of double field theorem.
So just one question. So in multi-integral rows, as I understand it, do I always need the anti-commutator? Keeping not to be 0? The way I usually think of multi-integral rows is the Haberstern notation.
Yeah. So usually you get it by some CPT or something. Yeah. So if you have a Q. Usually you do some CPT and then you get a Q. So it's like what happens in, let's say, Young's. You have a BRST and when you also have an NT. Okay. So this is set of results and the set of results continue. Okay. So then let me so this especially is true for this thing. So let me also start with Wald. At some point argued that the charge associated with thermal invariance with thermal or KMS invariance is same as at the horizon. This is again gravity. Is same as the entropy of a black hole. So this says that this Euclidean periodicity and this thermal invariance is very closely related to this entropy and being there. So,
I don't know what the KMS constraints are.
This is analytic continuations of Euclidean periodicity. So various real-time correlators are analytic continuations of Euclidean correlators. By inverse peak rotations, and the Euclidean correlators we know satisfy Euclidean periodicity. That is, you translate operators like beta, I beta, then you get back the same correlators. And that you can ask what it gives you when you analytically continue back into the real time. And it gives you something which is basically what are called KMS questions. So if you have an endpoint function which is analytically continued from a Euclidean correlator, Euclidean endpoint function, then the thermal periodicity of the Euclidean endpoint function imposes some constraints on the analytically continued real-time.
What are the nature of the constraints? Roughly.
So they are they say something like so you have these two copies of the operators, and they basically relate, let's say, OR at roughly or OL.
But this is not a relation down between real-time correlators, right? You're going off the real axis.
It is a constraint on the Schwinger-Keldysh correlators. In the sense that you can think of this as you can think of this as basically what you get. It tells you something about the analytic structure of the real-time correlators. If you analytically continue, okay, it says that like on the imaginary time there's periods.
But there's no way of putting a constraint just on the function of the one real variable.
This would imply something, not just.
So
right. So but I'm trying to understand what it implies.
Yeah.
So I mean, one can think of this as, I mean, you can kind of expand this, for example. Okay, let's say for beta small. Okay, you can say this is nice.
But also, what is O left and O right? Ultimately, you just have some operators, right, whose expectation values or correlations you compute. Right? This left and right refers to the two Schwinger-Keldysh
correlations, yeah.
So can one just phrase it in terms of some correlation functions in fluid mechanics in the end?
Yeah, you can. But not in completely in fluid dynamics.
Okay, or in the anyway finite temperature theory.
Yeah, so usually, like as I said, like what I said about this thing, that the K-means condition usually end up implying fluctuation distribution. Okay, so that's what you get. Like if you just expand to this expansion and so on, you get something like the noise correlators in fluid dynamics, which are not quite fluid dynamics. It's you are adding noise to the fluid dynamics, are related to the dissipative coefficients in a very specific way. Okay,
so the response to the noise. That response as specified through correlation functions gets related to
no, not response to noise correlators. Like like you measure some noise here, you measure some noise here. Okay. How is the noise here correlated with the noise here? Okay, that correlation is very much related to how like to a response, where like you put something here and then you measure something there. That's a typical kind of 2-point, and then there are generalized relations at 3-point. Okay.
Sorry, I don't really looking at the clock, but when I read Wall's paper, then I did not realize that Wall's nether charge is something associated with the K-means integral.
Yeah. So this is this thermal translations. So what Wall does is basically take the vector, which is the thermal vector, which is and then which is the killing vector of a particular solution. Okay, and ask what is the Noether charge associated with that.
Yes, he does.
The translation by that, on the solution. Okay. So roughly what Wall does is that what is the charge associated with invariance and the thermal translations.
Yes.
Okay.
By that you mean the del T. I mean the
1 by T del T.
Yes,
okay.
Sorry. Yes, indeed.
Okay. So I mean the 1 by T, Wall kind of doesn't put the 1 by T and then puts 1 by T in various places and so on and so forth. But the point is that like after you check everything, this is what he says. Okay. So it's a.
Okay. That gets related to the K in this case.
Okay. So this is a statement which tells you that this is and things here are related. That there's an entropy is related, and this is actually made. Okay. Then there's also a relation by Wilsonian and Baffa. Okay, which okay. Let me just say.
You have your 2 talks anyway, so just pace it accordingly. We won't get anywhere now.
I have not finished my introduction.
That might be a good thing to try and finish in talk 1.
Okay. There's this thing by Wilsonian and Baffa who showed that the entropy of certain supersymmetric black holes, these are actually flat space flat black holes. Okay, they are given by, they are reproduced by a double topological string theory. Okay. So this is very much like the thing that I just erased away, which is that there is some double theory.
Double the topological. I thought it was just topological, like type 2A theory or type 2B theory.
But you have to square.
You have to square the final answer. Partition function square. Oh, that's what I mean.
So this is very much related to various things that I was saying in the previous version of the board, which I just erased away, which is that you have a certain set of states. You want to count those states, you can write on a double topological theory for it. And what these people showed was that the entropy which is contributing to these supersymmetric black holes, which you can just count. Okay, which is and you can write on a double topological theory, but then the double topological theory is really just a double topological string theory.
This topological, the partition function is a mod square of the topological string. So it's like two copies of the topological string.
Yes.
So it's not interacting with each other or anything. That has different flavor from your Schwinger.
Yeah, it does not interact in the leading order. I mean, there's some. Yeah, it's not quite true that when you go to subleading order.
You mean OSV is not quite correct?
No, or it doesn't quite factorize.
Okay.
But anyway, no mind. But the point is that so which means that which tells you that trying to say that black holes are related to some kind of double topological theory, like the way that I was telling you, like it was. The previous argument was why double topological theories describe fluid dynamics. You can write down a double topological theory with these fluid dynamics, and this is a thing which tells you that why double topological theory can describe black holes. Okay, and this we already know. Okay, because of Wilsonian.
So OSV had some kind of a double of the cigar, right? I mean, I forget now what the picture was. So one half of that was a cigar, and some kind of a double of the right. I mean, there's something, they cut it in half and they got a cigar.
Yeah. So it's yeah.
So you're saying that is only some kind of a tree-level approximation, and if you actually go to there is some Legendre transform, right? I mean, they didn't quite do the full Laplace.
Yeah. So you have to work in a particular ensemble for the black holes. Yeah. So there's a various there's of course subject on it. But I'm just saying that it's not completely crazy, because you already know of an example where there's a double theory which reproduces the black hole entropy. It's a very specialist example, not in all qualifications apply. But string theory is already telling us that there's something like this is happening. Okay, and then there is a research by Anthony. Who wrote a paper a few years ago, okay, and showed with two interesting things, okay, and the two interesting things are like this. So, one thing that she showed was that existence and stability of hydrostatics is the same as second law.
And in particular allows you to construct an entropy current.
Yeah, and also an entropy current. So an entropy current plus the existence of entropy current plus. Let's go for the second definition. Okay. So what she basically showed was that this thing that is actually written down is so it kind of completes the set of things. Okay. And another thing that she showed, which is not quite very explicit, but this is something that she did show.
So that existence of hydrostatics and stability.
Stability of hydrostatics. Of the hydrostatics.
So you do fluctuations about it and all design are decaying.
And in some arbitrary background.
Yeah, in arbitrary stationary. Yeah, we are doing hydrostatics, time independent, and slowly varying, all that. You're not going away from fluid dynamics.
It's a proof or it's a conjecture?
It's a proof. It's a long-winded proof, that she just proved.
And that is equivalent to the existence of an entropy current.
And there's an entropy current which satisfies a local cycle.
Well, it's explicitly constructed using the data. Yeah. In fact, she considered an entropy current and an entropy current.
okay, she constructed was exactly like the wall thing. This is the current associated with thermal translations. There is no other current associated with thermal translations. So there's a particular formula she writes down in a paper there, which is clear that it's basically the way the current associated with thermal translations. Okay.
So thermal translation, do you mean the whole thing is formulated with the Euclidean periodic time?
You can do that, but because it's a time independent, you can go back and forth. I mean, we're talking about hydrostatics.
What does thermal translation mean if you don't have Euclidean periodic time?
Just an anti-continuation of it. I mean, yeah, so complex time. What I'm saying is that you can also analytically continue the statement. An analytic continuation is trivial in hydrostatics, in time independent situation. Because what you do is like, you're looking at fluid dynamics where beta is small. Okay, so temperature is large, which means that you almost get a thermal reduction, a conserving reduction on the thermal cycle. Okay, so like whether you treat this additional dimension which you have anyway thrown out as real time or imaginary time does not make much difference. Okay, at the end of the day, you have something happening on the station. But anyway, okay. So this kind of nicely complements what one did, okay, and it says that this is also the same thing. Okay, so let me end my introduction, okay, with saying one more thing, okay, which is something that I've already mentioned, okay.
But can I ask one more thing? Especially in thermal translations. Normally, at least in non-dissipative systems, if you have symmetry and you have an action, then neither tells you how you get a current out of that. So here, the analog of the action is the Schwinger-Keldysh or what?
No.
How do you go from this here?
Yeah, so here she was just looking at the equilibrium partition function. Okay, but you can also, this research has been generalized by us to even non-dissipative, fluid dynamics. You can just write on some general Landau-Ginsburg action, which I wanted to come to. But yeah. So.
No, I'm just asking because of the obvious points about this and so on. But you're saying,
so she proved it for the equilibrium partition.
There you get a current which is valid in general, right? That is for non-distributed situation.
Yeah, but if you have a Noether current, which is conserved, which you have, then you can just connect it to a. So she constructed an entropy current whose divergence is also possible. Okay, so it was this plus connected in very specific way in the presence.
And then she was saying that only the non-dissipated part of this.
No. So this statement reproduces the non-dissipated part. Okay, because this statement she got from a non-dissipated answer. Okay. Now and then she added some things by hand. So then, okay. A bulk of her paper was about constructing this. About removing all the non-dissipated parts, so that you can just focus on the dissipated. But anyways, so the last thing I wanted to say, by the way of introduction, is a statement by Subrat and Kyriakos, okay, who basically argued that the doubling, is what gives you the interior of a black hole. And the black hole function that. So this is a proposal, but I think for this set of ideas, okay, which basically say that all these things that I listed here are all very closely related to each other, and the real question is that so there are all these statements which basically link various things in one box to another box, various things within the boxes, and so on and so forth. The real question that is to construct a formalism, okay, in which all this is realized. So,
why did you put a question mark? Why did you put a question mark after realized?
because okay, do we have people who can be?
What is the next box?
so the question is that the question is really whether we can construct and on what the reason that for obvious reasons I don't usually tell all this stuff, but in the talks, but sometimes I just was telling you this because often there are various things they are doing, but I'm just trying to say that they are very strongly constrained. Okay, because we want to be consistent with all these results in various ways, and these are all very strong results and with very elaborate features. Okay, and it is not. It is difficult to construct a formalism. I think all the various statements, if you take the various statements that I've said, and if you take it seriously, it almost gives you a unique theory. Now, how much more time do you have?
So we can go to 1 o'clock, I would say, today, and then we can plan a second talk sometime tomorrow.
Okay. So in the remaining time, okay, since it has all been review of what other people have done, okay, let me end up with another review of other things, which is basically, let me just tell you some basic things about Schwinger-Keldysh. Okay, just write down some formula and not leave you with all these statements. Okay. So what I'm going to do now, in the rest of the time, is just talk about Schwinger-Keldysh. Just talk about my first box, and then come to my second and third boxes tomorrow. Okay. So the first box is about Schwinger-Keldysh. Okay. So what is Schwinger-Keldysh and what are the basic ideas behind it? What we do. So let's say you have a relativistic quantity theory. Okay, and you have a state, a mixed state, okay, at some time t equal to 0, which let's say we know 0 at t equal to 0. This might be normalized or non-normalized. So the density matrix, for example, for thermal guys, it's easier to take this to the power minus beta h. So you can think of this as the normalized it to get the density matrix. Okay, the actual density matrix, but so you have a mixed state which is denoted by a rho hat equals 0. Then now you're interested in correlators. Okay. The general correlator that we will be interested in are correlators of this type, where you take a case and you have this rho hat equal to 0, so you want to calculate the expectation value of certain set of operators. Okay, and the certain set of operators, let's say are let's say the anti-time order. Okay, operator. Okay, and then also some time order. So this means so this is the kind of, so let me call this as, so these are what,
and all the time ordered operators are to the right of all the anti-time.
All the time order operators are to the right of all the anti-time order operators, so and all the anti-time order operators are to the left of.
What is the subscript L, super L and R?
So I will just this is usually denoted by saying that so if I just want to, it's more convenient to write it as some Schwinger-Keldysh ordered guys, where I write down.
At this stage, it means nothing. It will drop.
Yeah.
Because the theory has some set of operators, right?
Yeah, just a set of operators. It just says that this label at this point just says whether when it appears in the correlator, you want it to be time ordered or anti-time ordered.
Okay, that's all.
Yeah. Okay.
Sorry.
This is the definition. Okay. What is the face this? Okay, Schwinger-Keldysh.
Heisenberg equation of motion for OL and OR. It's the standard thing. OL dot is the commutator of H.
Yes. Heisenberg equations are the standard things. The green functions have this time ordering and anti-time. Okay. So this is the kind of correlator that you want to look at, and and this I can write it in various ways. I can write this here and this here, but saying that by putting this L and R, I've told you what is the correlator I'm talking about.
And because you've got all the T's to the right, you can, in the trace, move them to the left of row. Right?
Yeah. So it's like this.
So you can think of one side being associated with the bra, the other with the K.
Isn't there a sign difference in the equation of motion?
Pass through.
There is a sign difference.
Trace.
There's
One is this way and one is this way.
Yeah. So there's a time difference in the sense that it depends on whether you go to T or minus T.
Yeah, that's what I mean. So in one formula, what are the equations? That's what I'm asking.
So the operators themselves obey the same equation, but you can kind of think of the anti-time ordered operators as time ordered operators with the time reversal. Okay. Yeah.
So this is one copy of a quantum field theory or two copies?
At this point, it is one copy.
It's one copy, and the L's and the R don't mean anything.
Yeah. So let me say this. Okay. That's it. This is so what L's and R's start meaning something here. Okay. It just tells you where to put these things to calculate this coordinates. Okay. So and as I said, Shira said, this is associated in some sense with the bra, and this is associated with the K. Okay. This is a K copy of the operators, which are time ordered, so the usual set of operators. And then there's a bra copy of the operators, which are anti-time ordered, which are here.
And the time is real.
Yeah, the time is real.
Yeah.
Yeah, the time is real at this moment, and okay. So this is the kind of operator that we're interested in, the kind of correlator we're interested in, and we can actually write down a generating function, like easiest way, as we know in quantum theory, is to write down a generating function which encodes all these operators, which is what is called a Schwinger-Keldysh path integral. Okay. So the way to do it is to introduce two sources. Okay. For these right operators and the left operators, okay, and the generating function, you can convince yourself takes this. So what this means? So this U is this unitary evolution, okay, which is of the quantum field theory, okay, which is some e to the power minus IHT. And of JR just means that, as usual, you change the unitary evolution, you deform the unitary evolution by adding some sources for some operators. Okay, so it's some unitary evolution in the presence of sources. Okay, and you have JR, and then you do the same thing for here with the dagger, and this dagger, when all the dust settles, if you differentiate this guy with respect to JR and JL and set the sources to 0, you would see that you basically generate coordinators of this. Okay. So this is also a definition. So this is what it's called as a Schwinger-Keldysh path integral.
So far, this is just follows from.
This is just follows from like I don't know.
This is yeah.
So I write down a generating function for these.
Yeah. So you could plainly take the T to the left.
Yeah. So take the T to left, and then you do the usual stuff. You have some correlators. What would you do in the usual failing correlators? You would have some time-ordered correlators, and the way to reproduce them is that multiply by some number of j's and exponentiate this, by summing all set of components, and that you can represent by a deformed evolution, unitary evolution. You deform it by some source, and you calculate some path integral with that, or some expectation value of that deformed evolution, and then that is basically the generating function for these correlations.
You mean just that is J5?
Yeah, JO.
So someone look, you have to break the unitarity to bring in dissipation, or you still keep an unitary evolution?
No, I think the unitarity needs to be preserved. Unitarity is very important. And in fact, I will tell you what the unitarity leads to. Okay, you don't break the unitarity. In fact, yeah. I mean, another way to say that unitarity is realized in long distances crudely by second law. Okay, so in some sense, second law imposes unitarity. Though it's not quite obvious first. Okay, so this is the set of path integrals. Now you can, given a quantum field theory with some Lagrangian, okay, you can do various things. Like you can do all the things that you learned in a quantum field theory course. Okay, to do these path integrals, the generating function, and so on and so forth. Yeah. Okay, and it is all done in the experts. Okay. So let me just. I'm not. So since I'm not teaching a course on Schwinger-Keldysh, I'm not going to do it. But it's all done. And you can just do it. So let me just say something interesting about this path integral. So something interesting happens if you align these forces. So let's say you said gr equal to jl equal to j. Okay. Then what happens is that this edge k in this aligned limit, okay, becomes just case of rotation equal to, and this is a equal to unitarity. That the u I have put here satisfies u dagger equal to identity. Okay, it's very simple to see. You say both the j's to be equal, then u of j dagger, you get to the other side, it becomes identity. Okay. So this I would say that it localizes to the initial state. Okay. So the Schwinger-Keldysh path integral, ZSK localizes to the initial state. That's one way of saying what I'm saying. If the rho hat is not, like let's say for the thermal state, okay, then this would be, if it was c to the power minus beta head, this would be same as ZU. Of the initial. So another way to say is that it localizes to the initial Euclidean density matrix or Euclidean path integral, which defines the rho. Okay. So for example, at zero temperature, you take some state with temperature T, some thermal equilibrium state. Then there's Euclidean path integral associated with it, which is just ubiquitate and put the time circle with radius 1 by t. Okay, and that path integral. So this path integral localizes to that path, reduces to that. Okay, so this limit. Okay, so in some sense you can also call it the topological limit. Okay. So one way you can realize this kind of a thing, and one way it is realized, for example, in the Martin-Sidiaros kind of constructions, is that like what you have is, as I said, you have a q and a q bar with q square, q bar square, q bar equal to 0. Okay, and q of the action is 0. Okay, there's q close, the action is q close. Okay, and this means that and what you do is like so there's as a lot of people are familiar with. For example, in the Young story, if you have such things, like you can use these Qs, these Fadi-Papa Qs, for example, localize your thing to just gauge invariant part of the path integral. Like, it just cuts down the gauge output. It's kind of gives you the exact what to say. You can add a Fadi-Papa action and so on and so forth, gauge fix, such that you localize onto just the gauge invariant part of the phase fix. Okay. So another way to say it is like you can also feel this by looking at the operators explicitly. So what you have is that in the action, okay, you have something like the coupling of the operators to the sources goes like this. Okay, this is because unitary is the usual thing that you have over GR, and because of the dagger, so the IS. So if you think of this path integral as some e to the power IS over fields, okay, over some double fields, okay, and d phi r, d phi l. Okay, then in this S, in the Schwinger-Keldysh action, the sources actually appear like this.
So at this point I have two copies of my field.
Yeah, because you have two unitary evolutions. So if you try to write down, you have two sources. Okay, so basically everything doubles. If you try to write down, let's say you have a Lagrangian for this theory. Until now, right? Assume, but let's say you have a Lagrangian for this theory and you want to write down these correlators. One way to write down these correlators is to write down something like this. Using the Lagrangian to write down some action, so that Lagrangian correctly reproduces, let's say, purely high-ordered correlators. And then, double everything.
So the two fields live on two different spacetimes.
But
yes.
The contour has to be different, no? Sorry, I'm confused. There is a contour, right, in the complex temperature thing. So the ORs or something live on one.
Yeah. So the contour associated with this thing that I've written down, you just look like this.
So you wrote this integral like this one.
Yeah. So this is your rho hat at equal to 0. It could be a thermal density matrix. That's why I'm representing it this way. Okay, so this is the insertion of the rho hat equal to 0, and here are the right operators, and here are the left operators. Okay, and the right operators, and this is real time. This is imaginary time.
Okay, this one. Where is the I feature?
Yeah, so if it was thermal, basically you would go around a circle there. But yeah, that's the trace. Okay, so
sorry, I'm still confused. Can you rewrite this integral but with the t's and the x's in place, just so I understand?
That's what I wanted to pronounce. Clearly the t is not the same.
you keep going on together.
No, I need in the arguments of the J's and the O's as well.
So, yeah. This. Well, in this I'm assuming that there's no CPT. Okay, so we said this is what it is.
Same x and t.
Yeah,
they're on the same size.
You can bring them to the same space. That's it.
I don't understand what that means.
Yeah. So the reason that you can bring them to the same space is that, they better live on the same space because you're in this space and this is these guys. Right? I mean, there's an identification here. That's another way of saying it. Okay. There's an identification on both initial time and final time.
I'm very puzzled about this contour picture, which is why I was asking. So they live on the same space. There's one Minkowski space.
There is Minkowski. So can be T mu, in which case it's not.
It's a complexified time, so its imaginary part is periodic and its real part is not. Is that?
It's imaginary. Yeah. Let's say if it is thermal density matrix, yes, its imaginary part is periodic. Its real part is not. And there's a condition. Okay. It basically says that the field at this time. Okay. And
this time is some real time with the imaginary part.
Yes. Okay. At some time is same as this left field at that time. That's a boundary condition, and then there's an initial boundary condition. That's a final boundary condition.
And I should think of that as t equals infinity.
Yeah, you can think of it t equals infinity. After you're done inserting all the operators that you want to insert.
So look at this. Extending to the imaginary axis is only at the initial point, right? T equals
yes.
That's the contour you are thinking. Not at every point you are going along the imaginary axis.
Yeah. So in that sense, so there are. See, the sources here are different from the sources there.
Yeah.
Okay. So the question of whether. So you can say that what I've done is basically I have just included all the difference between the two guys. Okay, I put the same coordinate system on both guys. Okay, some identification, and then I have some two different sources. Okay, and really and those get related because of these two boundary conditions. But in general, they are the same.
So if it was just an equilibrium partition function, the contour would just run around a circle in the imaginary.
Yeah, you would not have this.
If I wanted to compute correlators, let's say I don't want any of the T stars, I just want to compute those correlators, the contour I take is I run around the imaginary axis, and then suddenly I run along the real axis, putting in some O's, and then run back again.
Yeah. So the right operators are the time ordered guys. The time ordered correlator is just inserting on the right going contour, which will give you the right operator. The time ordered.
Sorry, since this was explained to me, maybe let me try to say it and see. So you would run, if you only had the time ordered guys, you would run along the top contour, inserting those guys.
Good.
Then you would turn around with that identification between the field above and below at the rightmost extreme, run back till the end, and then attach an evolution along the imaginary time to generate rho, which is e to the minus beta h. And so you go down, and where you ended would be where you actually started.
I still need the identification, because I'm still doing a path integral over exactly that field, so that identification is still...
Yeah.
The identification of the rightmost.
Yes.
The rightmost you would do that.
That's the point of writing it as one contour is to make that identification.
I see.
Yeah. So it's just this trace. I mean, I'm not doing anything except just taking this algebraic definition and writing down what is the contour that I have to evaluate the path integral in with the original Lagrange, single copy Lagrange, to get this.
Is this unique, this contour, or there are ways of...
So you can change the rho hat to equal to 0, of course. You can change the initial state. Okay.
And so basically what you're saying is that the contour is something like this, and then there is an identification very far away. Okay, sorry.
Yeah.
Imaginary time identification on the left is only when you have thermal initial condition.
Yes.
Otherwise,
Otherwise, you have to just insert the density.
So in particular, suppose that rho hat at equal to 0 is the pure state. Then you just start with some pure state. You evolve up to the whatever the latest insertion.
So the pure state,
and you fold back.
Yeah, the pure state would look like
Just write what you insert is psi.
Right?
Yeah, so that's how does the geometry look like? I mean, you start with some psi, and you go by inserting all this JL, whatever it is, and then you just fold back. But that's on a different. I mean, you have to think of two sheets of space-time, or not?
Yeah. So you have a bra and a ket. Okay.
Yeah.
A bra and a ket, and on the ket are the right operators, the time-ordered operators. On the bra, the anti-time ordered operators. You evolve the ket by the time-ordered operators, the bra by the anti-time ordered operators, and so on and so forth. And then, when you are done inserting all the operators of which you want the correlation function for, at some future point, you decide.
So you're saying at the limit, in the limit JL equal to JR, it looks like a single strip. Otherwise, it goes up like that, and then it sort of folds back along two different.
So another way to say it is JL is always become JR at, in the far future.
Why?
That's the boundary
condition. Unitarity. There.
Yeah. So the JL always becomes JR, and everything becomes, not the J1, so everything becomes equal. The far
future means very far away.
Yeah. After you have calculated all the correlators, all the operator insertions, everything that you have. Okay. And that is this. And that is just corresponds to this case.
Exactly.
Okay.
I have one last question. I have some, maybe I'm wrong. I thought the eternal black hole in ADS-CFT was sort of a way of capturing it. How do I see this identification of my left?
That's a very interesting question. I think the eternal black hole seems more like it captures something else, which you don't understand. Which is more of what people call a thermophyte double, where you take a square root of this and put the square root there.
You could take what you're doing here in the thermal case is going down in one shot. There's something that looks more democratic, that you go right, go half the way down, go left, go up. And if you look at the eternal black hole, it looks like the path integral version of that.
So actually different correlation functions.
Yes, different correlation functions, which is somehow related by conjugation in some sense. But not exactly.
Yeah.
So to extend the Hilbert space, you double the Hilbert space and take a pure
But
state.
that's a slightly different model. That doesn't work.
Yeah. But I never understood what happens in the far future there, which the black hole also reflects by just putting a single inside.
Right.
But
what I'm saying is the thermophile double is conceptually something else. You have an original system with the Hilbert space, you double the Hilbert space, you then take a pure state in the double Hilbert space such that were you to trace over one of them, you would get a thermal. But then in that pure state, you can do whatever you like. Right? It's a little conceptually different.
But isn't it exactly the same correlation functions if I get rid of all the far right states, just focus on the far right?
Not same as this. You have to break up that whole.
yeah. For thermophile double,
It's still the trace over the thermophile double. I think so just on the
Yes,
right hand
that is right. That would be the
That's
side.
right. Of the
Because it's
thermophile.
a way to generate rho by doubling and tracing.
So if I don't have any left state, I just have a right hand.
If you have the same watch.
No, it's not.
Because you have to move this through. Maybe.
No, it's not that.
Then you could just default the concept.
Yeah.
No, it's not O left and O right. It's if the O's only depend on one of the two Hilbert spaces. Since you're doubling your Hilbert space.
Is that not the same thing?
No, I don't think so. So the O left and O right is one doubling, but the doubling you need for the thermophile double is a different doubling, I think, conceptually. You double the Hilbert space, you take two copies of the same field.
but here you take a bra and a kit.
No, but it's not enough. You take the bra itself to be a product of two bras.
The trace of your thermophile double will be exactly this expression with square root rho, square root.
Yeah, which is
That's what you say.
yeah. So this is how thermophile double.
Square root rho.
Yeah, this is how you know like this.
What I'm trying to say is that this will be equal to that if all your operators lie in only one of the two Hilbert spaces.
Slightly different things.
If you have operators right in both Hilbert spaces, you won't connect to your Schwinger-Keldysh for one.
I think you would end up with this. Because the thermophile double also has a future boundary condition. Okay, the future boundary condition there is to say that like on the far future, you specify the final temperature is same as the initial temperature. You get a final thermal state, half thermal state, which is same as the initial thermal state, which is.
No, I didn't understand that. Thermophile level, you start with a particular state, and then you do whatever you like with it. What do you mean by boundary conditions in the far future?
That is not a completely well-defined problem. You have to give a future boundary condition for what you're calculating. Right? You have two Hilbert spaces. You have to tell me roughly how the original Hilbert space embeds inside this system.
No, I don't understand that.
You have to give it.
I'm sorry, let me just say this. Please do say. I have a system where I've doubled the Hilbert space, so that now in the doubled system the Hilbert space is well defined. The density matrix is a pure state, well defined. I can compute any finite temperature, whatever time ordered correlation.
But with what do you put on the right? It's like
you get what you get. I mean, you double the system, and then you do in that double system what you're doing here.
No, but like in ordinary field theory, you do a vacuum to vacuum correlator with whatever insertions you want. Okay, so if you did this state to the same state correlator with whatever insertions you want, that's what the black hole is.
I thought we were talking about trace
stuff. Suppose you find this formula and you want to ask what is the thermophile double interpretation of this formula? This formula with the square roots. Then I'll give you the thermophile double interpretation. Take your pure state on the left, the same pure state on the right, put whatever insertions you want. That quantity in the thermophile double computes this trace. And that quantity in the thermophile double is what's supposed to be the state of the black hole.
I mean, so it's actually different. I mean, okay, what is this object? Let me try to understand. You put two square root of those.
Why did you draw the contour for that?
This is something else.
That's what the black hole is.
No, but the thermophile double is this, but with a double Hilbert space.
No, but for instance, it's with the e to the power beta h by 2, right?
But in the double Hilbert space.
In the double Hilbert
Yes.
space. Well, Logan can explain it.
Yeah. So basically you have. So
Yeah.
this is the real time, and this is again imaginary time. Okay. Rather than considering that you go by beta by 2 down in the future state.
Oh, I see. Okay.
See, consider Euclidean path integral on S3 times S times interval.
Okay. I agree that the thumb of E double will be this.
Will be this once you say you put your insertions and sandwich both the left and the right with your particular state.
Yeah. Better.
Yeah, okay. All right. Sorry. Yeah. It's the same as this. Or it's in that contour with the double Hilbert space. That's what you're saying. Yeah. You can either use Loga's original contour.
Schwinger-Keldysh is original.
Okay. with the double Hilbert space or this. Okay. Anyway, this is equivalent. Yeah. But honestly,
no.
it's a well-defined thing. What is the future boundary conditions?
No, this makes sense only if you have final beta and there's only one beta in the problem. I don't know how to do fluid dynamics with this because fluid dynamics has beta which evolves with time. Okay.
No, but surely you should give me the.
Okay. Right now we're doing a formal question. You're telling me how to compute traces given a density matrix, right? If your density matrix is going to change with time, then okay, we haven't come to that.
No. This I didn't say anything about rho hat not changing with time.
No, I'm just saying you defined this quantity for rho hat at t equal to 0, right?
Yeah.
That's what you gave us a path integral.
But these operators are all inserted at any time and with
Sure. But
evolutions.
for a rho hat given at some time, right? Or forget even let me say for a given rho hat, right? So for that everything is clear to me. Now if you want to change rho hat as we go along, okay, then you have to tell me how rho hat is changing.
No, sir, this rho hat will change. If I calculate rho hat of t, because of the time relation operator, rho hat will change.
That is an independent equation, right? That rho hat dot is h commutator rho. That's an independent piece of data. Fine. That's what. Sure. Then you can. So you want to compute the same thing with rho hat of t now. But is that the point? See how it changes.
No. First of all, like the thermophilia does not calculate quite this. Calculates something.
Oh, sure. That computes it for a particular rho hat, time independent.
No. It doesn't even compute for rho hat. It computes this with square root rho and square root rho here.
But that is the same as in the double Hilbert space for a particular state.
Yeah. So it makes sense in the double Hilbert space. I don't know what that means in the single Hilbert space. Because in the single Hilbert space, this is a quantum field theory quantity. Rho hat and the calculating some expectation value. I don't know what it means to take a square root operators, square root other operator.
No, I mean this I don't understand. It means what it means, right? You do the square root. It's well defined.
It's well defined, but I don't know.
It's unnatural.
I don't know what the physical interpretation is.
You're saying you can't. Yeah. However, yeah. Okay.
What you're saying is that were you to change rho hat from in the double field theory from the original thermofield double pure state to some other state or density matrix, it would not admit this kind of a path integral representation.
Yes,
which is completely
no. So even in the thermal theory, this is not quite calculating something that we would usually measure. Right? It's calculating something which is an analytic continuation of things that we measure.
I think it's not quite computing the time evolution of the density.
Yeah.
However, fluid dynamics should allow you to compute everything here as well. So it might be, one shouldn't be too dogmatic about it, right? It might be a nice representation. That quantity might be useful part of it.
But I don't know how to do it.
That's the separate question. Nice.
I mean, nobody knows how to do it. I mean, nobody does. Nobody calculates viscosity in this, for example. I mean, I don't know.
But ADS-CFT likes that. That's a sign that something.
It's not quite clear. I would say that ADS-CFT, the classical gravity we think likes it, but it ends up with a future singularity inside. So it already tells you that there's something funny you're doing in the future which you're not doing correctly. You have to do it correctly in the quantum field. Okay.
Sorry, but I haven't understood. There's a mathematical proof that this integral representation is the same as that in the double theory and so on.
No, it is analytically related. They are related to analytical.
I'm sorry. I mean, isn't it a mathematical fact that I take the double theory in this pure state and I trace over the first of them and I get a density matrix for the second? And this integral representation is just a reflection of that. So what is that? You'd use this or that for viscosity, you've got to get the same answer.
Okay. The question is that how would you define viscosity? Because usually the viscosity is that start and finish some temperature state, something. You end up with some temperature state, and you ask what happens. Okay. Now how do you set up this problem?
Why can't you set it up?
You can given the conformal field theory on the left and the right.
And see both left and right sides.
Why can't I do that? I mean, there is a.
I
can set it up here, and there's a mathematical identity which will give me something here, right? Or it will give me just this contour.
Yeah, but here, it's. I mean, the basic point is that the only things that I know about this is useful for is to calculate quantities about the molecule. Okay, I don't, I don't think that for anything else, it's an in principle probably analytically continue this thing, but in practice it just.
But viscosity, just to talk about that specifically, is linear response about thermal equilibrium, right?
Yeah.
So you should be able to calculate it here, or
you do it by. Yeah, so
sure you can. You can.
You have to analytically continue.
I agree.
To 10. Then you're the city.
That's what I don't understand. Why can't you do it literally in this contour? I mean, there's an equivalence.
Isn't that lower
For
contour
any
coming
offset
back at
operator,
minus I beta by 2 or something? It's actually in the complex pattern.
Maybe it's
the same.
with OL.
Somewhere in the imaginary.
I think what Loga is saying perhaps is that if there are no JLs around, then those two square roots of rows they get combined to give you a single row, and then that becomes the same thing. So he's not disagreeing with that. What your statement is that suppose there are no
viscosity is a
OLOOR object. So then this equivalence is no longer true. Now I understand. Okay, sorry, I'm sorry. Now I understand. So then you have to go back to that because that's clearly correct.
I think there's a more basic question, which is we weren't really told why you needed to compute these correlation functions to begin with, both anti-time ordered and time.
Because I think this is the thing that you start with some mixed state and you hit with it. This is what you would calculate. You calculate some time ordered.
Why with time ordered and anti?
Yes.
Why?
Density matrix.
Yeah, because you have a density matrix. The time ordered in usual theory, but the reason in the usual testament showed that we don't worry about anti-time ordered guys is that anti-time ordered guys are related to the time ordered guys by a simple complex conjugation. Because the vacuum is a nice state. You're basically calculating vacuum to vacuum. For anything else, the time ordered correlators and anti-time ordered correlators are still kind of in some deep way related by the properties of the initial state, which is what I'm trying to capture here. Okay, but the point is that it's non-trivial. Okay, so it is better to keep both of them.
I think it's a more basic question. If we're doing linear response, I want to compute a 2-point correlation function. It's the retarded correlation function.
Yes.
And if I want to map that to time order, it's these kind of guys that I.
Yes.
Yeah, that's what was my confusion. Sorry.
Okay, so let's say
very same.
I think one thing that happens is that neither the regarded nor the advanced correlator actually cares about the initial distribution. In a theory, it would basically just depend on the evolution operator and not on the initial conditions that you are putting, which I guess is what we will come to next.
But the thing is that so I can tell you the answer. Okay, and I can tell you later at some point why that answer is true. But if you calculate average into difference, like O right plus O left by 2, let me call this average operators, and O right minus O left, let me call them difference operators. If you calculate the correlation between the average operators and the difference operators, you get retarded correlators.
Could I make one more comment about this? It's a general fact about quantum field theory that path integrals choose a particular order. That ordering is contour ordering. do a quantum field theory along a particular contour, the path integral will automatically order your operators. Now you have particular other ordering in mind. How do you get that out of path integrals? The way you get that is to go forward in time, then go backwards in time, so that the ordering along your contour maps the ordering of your physical quantity, and then go back forward. So let's say just in vacuum to vacuum, I wanted to use a path integral representation to get some ordering of correlation functions that I wanted. O1, O2, O3, which was not time ordered. I would insert O1, then go back down to insert the O2, and then go back to insert the O3. So it's just a general fact about quantum field theory. If you want a path integral representation of ordering that you want to put rather than what path integral wants to put, you have to do this contour zigzagging roughly as many times as the number of operators that you have. And that's at play here. As you said, the retarded correlator is a particular ordering of correlations, which is not contour ordering along one contour, because it has a commutator, right? So O1, O2 minus O2. One of these is time ordered, the other one is not. So you have to go back down to get the right ordering. So this is not particular to thermal physics, just a fact about ordering and path integrals.
That is true, I agree with you, but in particular, I was not able to see why the retarded is one insertion of T and one of T star.
So let's take
not one insertion of T and one of T star. It is average into left.
No, why is it okay? Why is it average into different? Sorry, I wasn't able to see that.
Okay, so there's a Let me give you a quick argument. Okay, so if you have like some number of, let's say you go to the average difference basis, where you have a bunch of average operators, bunch of difference operators. There's a theorem which says that like a difference operator, if it is a future-most operator, then the correlator is 0. The reason is basically because if there's a difference operator which is just here, if there's an OR minus OL with the same operator, you can just write it down. Okay, and the correlator is 0. So which means that like a difference operator is always should have some operator to its future for the correlator to be non-zero. Okay, so consider now a correlator like this. Okay, let's say OR minus OL. Okay, so this would vanish if this guy came to the future. Okay, which means this guy should be in the past. Which means this has, let's say this is x, this is y. This means this has a theta x greater than y. Okay, times something, and that's exactly the retarded correlator. Okay, so so that's how you reproduce retarded advanced correlators. You want an advanced correlator, you just
Well, there are two terms. Right? It's O1, O2 minus O2, O1. One of these is a time order. The time order guy goes along the first one.
Yeah.
The second one is anti-time order. That has to go along the second one. And then you process that, and that's this.
Yeah, you can like expand it out and use this definition to write it in terms of time order. Okay.
So maybe I'm sorry, then I'll do it myself. But so you're saying you can write it as either OL.
It's OL
minus OR.
Yeah.
And yes. That is the same as that didn't seem, because here
no, you have to do OR.
Yeah, here it's OR. Well, that is what is the kind of.
So it's OR minus OR. OR.
This is the part which was.
Wait. No, why did I get that wrong? That also has the right ordering and so how would we decide? Sorry. Okay.
Yeah. So anyway, so where were we?
So what you're saying is that if you have a density matrix formalism, you automatically have a non-zero viscosity by calculating this correlation for small frequencies.
Yeah.
Correct statement.
Yeah.
The doubling actually enables you to see that. That's what you look at. You're just trying to look at it.
Because you can look, because it's a question of calculating retarded correlations. Okay, so the point is that so let me just say what I was saying, which is that when GR is equal to J, L equal to J, then then this path integral collapses to the Euclidean path integral, and you can ask what happens in this case, and what you get is basically that this guy becomes something like J into OR minus OM. If you put JR is equal to JN, okay, and hence good. So basically that means that you have these correlators that the ZSK calculates. So the ZSK of J is really a generating function for different correlates of difference operators. Okay, and what you are saying is basically if you have a TSK, some O1R minus O1L, O2R minus O2L, and so on, and that is equal, right? Or that is same as the initial, what you calculated the initial. Okay. So what this tells you is that in this limit, okay, when you align the two sources, this path integral localizes to the initial state, and the difference correlators just localize to the initial correlations. Okay, that's where they're in the initial density matrix. Okay, this makes sense. And that is basically the thing. And so you want to basically say that these difference correlations are in some sense protected operators. They are just completely determined by the initial correlations, and they don't change with what what are the other things that you do. Provided you have aligned the sources. Okay, you can put any J that you want. Okay, and that can be realized in a theory like this, and it is realized in the multi-stage arrows by saying that these difference operators are actually Q of something. They're actually Q exact objects. Okay. And if they are Q exact objects, then in this correlator you can just take them as Q of something, Q of something, Q of something. And exactly like how you would prove that if you have a longitudinal photon in QED that it decouples, it does not quite couple to anything. Okay, it just decouples from the theory. These difference operators also decouple because they are pure gauge transformations.
Wait, now these difference operators decouple in correlation functions of other difference operators.
Yes.
But they don't decouple in correlation functions involving some operators.
Yes.
So in that way it's different from BRST.
In that way it is different from BRST.
Where the BRST exactly is decoupled in every correlation.
Yeah, and the difference is basically due to the fact that the average operators, which are the other kind of operators that you can insert, are not Q closed. Yeah. So you want your action to be Q closed. Okay. You want your difference operators to be Q exact. Okay. But you don't really require your the operators that you insert and the things that you calculate to be Q closed also. Yeah. I mean, which is what we usually do in the gauge theory, where the correlation function we are interested in are also like gauge ingredient correlation functions.
By the way, what are the Q closed operators in this situation? What is the cohomology of Q in this situation?
The strict cohomology of Q is actually trivial.
Zero. That's why.
Okay. And not Q alone, but QQ bar. In fact, the QQ bar makes sure that there is no funny cohomology. Right. That's what this doubling is sure. And what this does is that, so you can kind of write out a theory which does that. So since I'm already running out of time, let me just end with an example. Okay, which is this scalar field theory, and I'll pick it up from there, and how this works for scalar field theory. So the usual scalar field theory, let's say you have some scalar field theory, the single copy action is this, the Feynman path action is this, right? Okay, with a half and so on, which you keep track of. Okay. Now what you do is that you have to double this, okay? And you have to double this in a way such that you have this Q and Q bar and so on. Okay, and the way to do it is to actually so with every phi you have to associate the phi r, the phi l, and then the phi r minus phi l should be Q of something. Okay, so let me call it C bar. It should be Q bar or something. Let me call it C. So you have like C and C bar. Okay, to make sure that these guys decouple, right? Okay, and so you have these guys, and actually the best way to write them, okay, and do then is to actually write down in superspace. So you can write down something like this. You can have half. You write down a superfield capital phi.
I'm really sorry we are running out of time, but what is the argument we have to decouple I thought you just told me that viscosity required one insertion of the difference with an average. Then I got confused. There was something.
Pure difference coefficient. Difference with differences.
Oh, difference with
Average
difference.
not
Difference with difference. Okay.
Yeah, so some of the difference operators are like the chiral ring. So within themselves, they're nice objects. Correlations of themselves are nice objects. But if you put something which is not chiral, yeah, of course, then they can do some very interesting things and very naughty things. Okay. So it is in that sense that I'm saying that the difference operators are like, some kind of a chiral ring of this Schwinger-Keldysh theory. Right, anyway, but the point is that they decouple in that sense. They just encode the initial correlations. Okay, so if you write down an operator like, an expansion like this where your theta and theta bar squares to 0, and you take theta and theta bar to be minus theta bar theta, so there's just some superspace. So apart from x, you just this thing, you can define a phi like that, okay? And then you can define an integral in the superspace with the same kind of an action for the one copy, and that I play the Schwinger-Keldysh action. In fact, you can do this integral. Okay, this is a Grassmann integral where basically the integral over d theta is del theta.
Is it del phi square or is it some analog of the chiral phi d terms?
No, this is del phi square. Yeah, this is del a. Del mu phi square. Okay, so if you do it, you will see that if you substitute this is a simple exercise. You will see that you get something like this. Del mu phi r square, del mu phi l square, plus something like c bar square.
So you get a sum times difference term and a c bar.
Yeah, sometimes difference is just the right minus terms. So this, is what you usually call a Schwinger-Keldysh path integral, and the way you get this Schwinger-Keldysh action is by basically taking this Riemann action and adding to this. Okay. Now you can also add other terms because now we have like a additional theta bar. Okay. You can add, for example.
Sorry, how is Schwinger-Keldysh action related to your original scale?
It is related this way. That so it's like this action. So in some sense, this is the U2 JR, and then this is U dagger JL. Okay, so this is like the right minus left, and it is just correct kind of goes, so that the decoupling works correctly.
Are you worrying about the minus sign?
I'm worrying about the minus sign of the C's and the right and the left subscript. I just don't understand it.
This is something you take that, you replace phi by your capital phi, and what you
You work in one and forward and the other backward.
Yeah, it's true. But as a path integral, will have some convergent property.
No, the path
Technically, it's just the usual Euclidean one here, so that's fine.
Yeah, so
So if I just do this path integral over these fields, insert in a JR phi r plus a JL phi l, this will compute Schwinger-Keldysh propagators for the original scale.
yes.
And what are the C's do?
The C's at this point for this theory they just decouple, like because they don't quite work. Okay, but in general you need to have those C's to make sure that the general property that they say are still true. Okay, so
this would be true for any non-equilibrium. This is just Schwinger-Keldysh generically,
Yes.
not close to equilibrium or anything.
not at this point.
Yeah, not at 2 minutes.
Yeah. Okay, not at this point. Okay, so the close to equilibrium. I don't think I'm not close to that.
No, I just wanted to mention that this is true for.
Yeah, this is true for general thing. And then one thing you can do is that you can add something like del theta phi, del theta bar phi to the action. Okay, and what you can check. So what I mean is that so this is d square theta d2 phi dx. You can add that to the action, not just del mu phi squared. Okay. Then what this will do is it gives you actually a dissipation, linear dissipation. So this is also inverse. Actually, yeah, maybe I need to start.
why are these d thetas, Loga? Usually the supersymmetric action you don't put del theta.
Yes. Okay, yeah, that's what I was trying to do. So if you have something like this, let's say some vector times okay, then you can show that this gives you linear dissipation plus Gaussian noise, which happens by fluctuation dissipation with beta as the inverse equation.
Let me understand this Gaussian noise.
Yes. Can you explain that?
I mean, this is just a classical thing. So let's say just at the classical level, there's some classical theory. By Gaussian noise, you mean that there is a separate kinetic term for that. What do you mean by Gaussian?
But what I mean by Gaussian noise is that if you calculate correlators in this theory, okay, the correlators in this theory can also be computed by by taking a Langevin-like description with some linear dissipation in the Gaussian noise. You can think of that as the if you wish the stochastic quantization interpretation of this action.
I see.
So you exactly get this action. So can you write down the Langevin equation that you just mentioned?
The Langevin equation you would get is that
for this field theory.
Yeah, for this field theory you will just get
equation of motion equal to some.
Yeah, so the del square phi is derived from that. Okay, you can add a term if you want. And then you would get something like beta dot del phi.
Yes.
Okay, and then you would get this. You can kind of do a Hubbard-Frednovich here.
Yeah.
Okay, and
Wait, is this phi left, phi right? What?
It's you can think of it as a phi right plus phi right.
Okay, so phi sum. You're writing down an equation for phi sum.
Yeah.
And that on the right hand side, what is that?
Yeah, so what you can do is that you can introduce, so this guy, you can kind of do a Hubbard-Frednovich and decouple. And so the statement was, I was trying to write in the Langevin equation. And the statement is that this is a noise. I'm introducing a noise, which field, like this is the Hubbard-Frednovich field, which basically satisfies something like
Is this the same thing as saying that the right hand side for the equation of motion for phi plus is something involving phi minus, and phi minus has its own path integral which generates whatever means?
Yes. Yeah.
So that the phi plus couples with phi minus, but phi minus is on its own.
Yeah, and phi minus is basically it's weighed in some sense by this Gaussian answer.
So just to be totally clear, if you just wrote down the equation of motion from your Lagrange without doing any Lagrange transforms, anything, you get this, and what would you get on the right hand side?
You would get some phi difference.
Phi difference, and then the equation of motion for phi difference would be what?
There's no equation of motion for phi difference. The phi difference is just chosen from an answer. This path interval just weighs phi differences by choosing it from some.
No, but if I've got a classical Lagrange, I can write down an equation of motion for phi difference, right?
Yeah. So you would.
It'll be del square phi difference, presumably, or not? Will there be a kinetic term?
Yeah. So you would get an equation for that phi difference, which would be, let's see. Okay, this action which is shown on the C's is actually just phi difference times this guy.
Of course, you will get a kinetic term, right? Because
Just phi difference.
if there's a cross term, there's a cross term. But you get the same thing? But no, I don't. Sorry.
So the action that you'll get is just phi difference times this left hand side.
Yes.
Square, and then phi difference squared, which will give you this phi difference. Right? This is the equation of motion of phi difference.
This is the equation of motion for phi difference. Great. So what's the equation of motion for phi plus?
So if you do the equation of motion of phi plus, then you would get del square phi difference.
And the reverse and an anti-friction term.
Yeah. So you get what is called as an adjoint.
Del square phi difference minus beta dot del phi difference is equal to 0.
Phi difference is equal to phi difference.
Is equal to phi difference.
No, is equal to 0.
Is equal to 0.
Yeah.
And this, there's some path integral that generates the solutions of this equation, and that's what we call the noise.
Yeah. So this phi difference, and again, let me just remind you, we have to impose that the phi difference vanishes in the far future. That's the Schwinger-Keldysh boundary condition. Okay, and that this is some homogeneous equation, and and if depending on the initial state, it will give you something. Okay, so if you take initial state which is a thermal state, then you would just get this noise.
But this noise looks like very complicated noise, right? It doesn't look like this white noise there. So based on some interesting differential equation.
What's the correlation function of noise?
Yeah, so the phi difference itself is a complicated thing, okay? But after doing a Hubbard-Stratonovich, you do get
white noise.
White noise.
And the thing that appears on the right is the thing that has white noise. I see. So it's like a differential operator acting on this stuff. I see.
So, and beta is just a time-like vector.
Beta is just a time-like vector.
Which is just time in the simplest case, right?
Yeah. You can just take it to be 1, 0, 0. Make it non-relativistic.
So you mean Hubbard-Stratonovich field condenses? Is that what? I mean, how? I didn't understand the.
Sorry, I'm being very schematic about it, but. but this is you can do it. It's not very complicated.
I mean, it doesn't look like phi difference. It doesn't look like having a delta function thing. Phi noise has it, a delta function thing, but the phi difference seems to be propagating. Yeah, field.
But noise can propagate logically, certainly.
No. But that is phi noise equal to delta.
It needs some transformation. That's what.
Transformation or just some differential operator.
See, if you integrate out the phi noise, the theory that you get, okay, is the theory that is there. That's the state.
Mustn't it be the claim that basically what appears on the right hand side is the same differential operator that would make the Green's function simple? Because roughly there.
I would be happy with that.
Yeah.
I just didn't understand the identification of the phi noise with the phi difference.
No, I'm not saying phi noise is
no, not identification really, but you're saying phi noise is some kind of Hubbard-Stratonovich field.
Associated with phi, maybe.
Associated with that, and
it's kind of in some sense a conjugate.
That does not have a kinetic, that doesn't have propagating term. That's why it's a delta function, and just like any Hubbard-Stratonovich will have. Okay.
Right.
That will decouple the difference and the average.
And should be possible to say without any Hubbard-Stratonovich. Right? Just that differential operator on phi noise that has white noise correlators. Because you can calculate the correlator of phi noise. Right?
Yeah. So in fact, in fluid dynamics, that's what it will be. That, but the point is that you can just analyze this action. Okay, and it is this kind of terms that give you.
And what are the interpretations of the C correlation function?
So C correlation functions are just there to make sure that
C fields are there. But what about the correlation functions of C? Are they interpreted physically?
There is an interpretation of the C fields. Roughly they kind of the spectrum of the C fields tell you the Lyapunov exponents in the theory and so on.
So the physical.
There's some interpretation of them. But they kind of enter into this theory, to make sure that the decoupling works. And I think that is already too much of this thing. But anyway, okay. So let me just finish here. So let me just say what are the various things they said. Okay. So one of the things that I was trying to say was, like I was trying to say about Schwinger-Keldysh, fluid dynamics, and so on. And what I have, after enumerating various things that relate various very essential features of Schwinger-Keldysh, what we saw was that, so we did to Schwinger-Keldysh, try to understand what the formalism is. And though I have covered much less than what I wanted to, but I've said basically the essential things, okay, that you have some kind of a doubling, and like often you have to add both to make sure that there's a decoupling of the difference operators, okay. And an example is just scalar field theory, where you start from scalar field theory and you add some dissipation, and then you add terms like this, which give you some dissipation is equal to fluctuation dissipation. Okay, but
Just one question. So if you have compact fields, how does the future identification work? Let's say if it's just a phase field up to 2 pi, or it has to be 9?
Well, in general, there is an up to 2 pi. I mean, this also, you can generalize it. Question a bit, say that if you have a gauge invariance, how does it work? Then what happens is that, like the del thetas all become, the cubes kind of mix with the actual BRST cubes and so on and so forth. In some very interesting way, but in some sense it's understood. In fact, that's what Pavan did, because there they were trying to understand the instant-on solutions. There's some gauge invariance and so on and so forth, which you have to take care. There's a formalism to take care of it, which is goes by these mathematical constructions. Yeah. Okay. So let me stop here and thanks.